Welcome to qnawire.
Okay, so this is a classic example of a vector decomposition in 2 dimensions. So to get started, let's go ahead and draw a little free body diagram of what's going on. So we have 2 different vectors. We can label them F subscript R for rover, and then F subscript F for Fido. And then we're told that they form a 90-degree angle in between them. So we're just going to go ahead and call that angle theta. Okay, so this is what a bird's eye view of those vectors who are pulling on the point right here look like. But we're going to use the head to tail method of vectors in order to make this a little bit easier to understand. So let's go ahead and transcribe that rover vector over, but then we're actually going to shift the position of Fido. So that vector is going to go over here. So that we can add these vectors together and then show the total vector, which I'll draw in a different color over here. So this is going to be the sum of F rover and F Fido. So let's call this F tote, and then go back and draw FF in here for clarity. And so the position of theta has also shifted. So in a dashed fashion, we can show a nice right triangle over here. And then our angle theta is now over here. So another reason why I broke that down and introduced those dashed lines is because in order to do vector addition, we're going to have to decompose FR and FF into their components. So at this time, we now need to define a coordinate system. So I think it would be most convenient to set the x-axis along the direction of rover and have the y-axis be perpendicular to that. So with that being said, in the third color, we can now show that horizontally, this is now going to be the x component of Fido's force. And then upwards right here, again in our third color, we have the force of Fido in the y direction. There we go. So that is all the vector decomposition that we're going to do. And the last thing I'll note is that in the second half of the problem, if you think of this as part A and part B, then we need to find the angle that the resultant force makes with Fido. So we can go ahead and define a second angle over here. And I'm going to call that phi. And then we'll return and solve for phi a little bit later on. But anyway, starting off with part 1, we need to remember some basic trigonometry, some basic geometry, and note that the y component of Fido's vector, Fy, we're going to have to use the sine operation here. And the reason for that is because we are essentially dividing through opposites over hypotenuse. So that's why sine is going to show up here. And then likewise, by process of elimination or by memorizing that you take a cosine when you want to find the the adjacent over the hypotenuse, that is going to give us a cosine. Alrighty, so these are a pair, so we'll draw some little braces around them. And then we have already chosen, we conveniently set up our axes so that the x-axis will be along the direction for rover, but just as a formality, let's also technically break up rover's force into its 2 components. So you can think of it as a 90-degree, or rather, sorry, 0-degree angle. So the sine of sorry, as a 90-degree angle. So the sine of 90 degrees is going to give us back 1. So in other words, the x component of rover is just the entire force of rover. And then the y component of rover is going to be 0 because there's no vertical component to rover's force, big fat 0. And those two to go together, so I'll put those in braces. So now that we've decomposed those two vectors into their component parts, we can now go ahead and add them together to find that total vectors, individual x and y component parts. So the total vector in the x direction is going to be the sum of the x directions of the two constituents vectors. So that's frx and ffx. So we can go ahead and substitute those in there. So that was, again, the entire rover force added to the sine components of Fido's force. And then over here, we'll do F total for the y direction. And that's going to give us rover's y direction plus Fido's y direction. And then remember earlier we said that rover's contribution is 0, so we're only going to get the Fido component, which is the cosine. Great, so we are running out of space. So we're gonna add a new slide soon, but just keep those two components in mind because we have the x component, we have the y components, and then now we're going to go ahead and use the Pythagorean theorem to put those together in order to say that the total magnitude squared is going to be equal to the x and y components squared added together. X direction. Okay, so hopefully you have those two components from before written down. So let me, at the same time that I substitute, go ahead and take the square root of both sides. So we're going to get like a crazy huge square root in here. So what goes inside in parentheses is the force of Fido's sine component, theta squared plus the force of rover added to the cosine of Fido squared. And that concludes our square roots. Now we can go ahead and plug in some numbers. Recall from the beginning that Fido's force is 300 newtons. I'll put in the sine of 60 degrees in there. Added to rover's force, which was 270. Added to 300 of the cosine of 60 degrees squared. Yes, okay, crunch that into a calculator and then express that in 4 significant figures. Don't forget your units, working forces. So in SI, that's going to give us newtons. So at the end of the day, you get 494 newtons. Okay. All right, so that is what we're going to call part A of the problem. So magnitude of the resultant force, we already did that. Let's call that part A. So now let's move on to part B, which is to find the angle that it makes with Rover's rope. So remember, we defined the angle earlier is that phi angle over here. So take a quick look at the diagram. And another convenient reason for saying Rover's force along the x-axis in the beginning is now phi is going to be the angle between our resultant vector and the x-axis. So in other words, we can just use the tangent trigonometric function to say that the tangent of phi is going to be the opposite over adjacent. So in other words, the y component over the x components. Let's actually get a third slide in here. So everything that I just said, let's encapsulate. Phi is going to be equal to the arc tangents of the total vector, sorry, the y components of the total vector divided by the x component of the total vector. And then just refer to your the diagram that you drew earlier on the previous slide for why that's the case. Remember that tangent is adjacent, sorry, opposite over adjacent. So now we can go ahead and start substituting in more specific quantities. So remember that the y components of the total vector was just the sine component of Fido. So it's going to go in here. And then the x component was the sum of Rover's force added on to the cosine components of Fido. Big close parentheses. And then lastly, we can plug in numbers. Part B is going to go a lot quicker than part A because we did all the setting up earlier. So this is part B. And then we're going to have same numbers, 270 plus 300 cosine of 60 degrees on the bottom, and on the top, just 300 sine of 60 degrees. Plug those bad boys into your calculator, and then to 3 significant figures, the angle that you'll get is a nice 31.8 degrees. And there you have it, part B, part A, and then our figures. Thank you.